Here in section 7.8, we'll be looking at improper integrals, and these will be coming in two different forms, or we'll study two different types of improper integrals. And the first type will be to consider an infinite region. So in other words, we're finding an integral over an infinite region. So typically we've considered integrals over a finite interval, or I should say an interval of finite length. Now we want to consider it over an infinite length interval. So let's consider an infinite region S, which is bounded by the curve y equals 1 over x squared, the x-axis with x greater than or equal to 1. So does this region have a finite area? Well, let's think about how we can solve this problem. To picture it, so we imagine the graph of 1 over x squared here, which will be this decreasing graph, and it'll tend towards 0 as x goes to the right. And we're considering the region that it bounds between the x-axis and the curve, but only for values of x that are greater than or equal to 1. So it's just the region here. So one way to look at it would be to choose a right boundary for the region and make that right boundary a variable. So in this case, if I choose the right boundary to be some variable t, then I have the finite area of this region would be the area from 1 to t. So we can start with this problem here. So to find the area of the finite region, under the graph of 1 over x squared, on the interval 1 to t, we can find the integral from 1 to t of 1 over x squared. And essentially what we're doing here is we're getting the area of this region, this finite region. We'll call this area A of t. And so this area will be a function of the variable t. So let's work it out. We have the integral of 1 over x squared, that's the integral of x to the negative 2 power, will be negative 1 over x. And then we'll evaluate from 1 to t. And so we'll have negative 1 over t minus negative 1, so it'll be plus 1. So I'll write it as 1 minus 1 over t. So we see here that as t varies, as we change t, we can get different areas. So what happens as t goes to infinity? So we can now consider the infinite region, under the graph of f of x equals 1 over x squared on the interval from 1 to infinity, has area given by the limit as a of t, right? So that would be from 1 to t. So we take t to infinity. So the limit as t approaches infinity of a of t. So given by this limit, we get the limit as t approaches infinity, 1 minus 1 over t. And of course, as t goes to infinity, 1 over t goes to 0. So this limit equals to 1. So what we see here is that the area of this infinite region under the graph of 1 over x squared from 1 to infinity has a finite area. So if this region were to extend to the right forever, it would have a finite area equal to 1. Even though it's an infinite region, right? The boundaries of this region are essentially unbounded. It has an infinite area. So is this a paradox, or is this some sort of logical mistake? Well, the answer is no, it's not a mistake, and the reason this happens is because essentially if we were to go far enough out in this graph that the graph would get so thin that essentially it would be really close to 0. So imagine that we were to continue this decreasing graph really far out, that the graph would essentially have very, very tiny area, and so the contribution to the overall area at those very far distant tail ends would be very little. So this kind of is one way we can imagine, or we can think about this first type of improper integral, is to integrate over an infinite region. And so essentially what we just did was we computed an integral of this type from a to infinity. So as long as I have a function f of t that exists for every number, an integral from a to t of f of t that exists for every number t greater than or equal to a, then the integral from a to infinity of f of x dx is equal to the limit as t approaches infinity of the integral from a to t of f of x. Okay, so when I put the infinity in the upper limit in this case, what we're really doing is we're taking a limit as that upper limit approaches infinity. On the other hand, if I take an integral from negative infinity to b, what we're really doing is we're essentially taking the limit as that lower limit of the integral approaches negative infinity. Okay, so you can imagine the picture here is that I've got some function, say from a to infinity, so we take a finite region, take the area of that region in terms of the right endpoint t that's defined as a some value that can vary, and then I take that value to infinity. So essentially it's stretching that area out, and in this case it could be a finite number or it could be infinite. This area could be infinite. So in the second case here we're looking at some region here where from negative infinity to b, some other point b here. Again, we're taking this finite area from t to b, but then taking t to negative infinity. Okay, and so that would give the area of, again, this infinite region. And then putting these two together, we can form the integral from negative infinity to positive infinity. So that would be basically integrating over the entire real number line. Okay, and so we've defined that as the integral from negative infinity to a plus the integral from a to infinity. And the a in this case here is chosen arbitrarily. So this a essentially can be any value. Okay, Now in the case when either of these integrals from a to infinity or from negative infinity to b are equal to a finite value, right? In other words, if these corresponding limits equal to a finite value, then we say that these improper integrals are convergent. On the other hand, if they don't exist or they equal to infinity or negative infinity, then we say that they are divergent. So let's try a simple example. And here's just one way we can visualize it. And it's finding the area of an infinite region. So what about this integral here? So the integral from 1 to infinity of 1 over x dx. So we'll define this as the limit as t approaches infinity of the integral from 1 to t of 1 over x. And t approaches infinity. We know the integral of 1 over x is ln of x. And then we'll evaluate from 1 to t. And so this will be the limit as t approaches infinity, ln of t minus ln of 1. Okay, well we get ln of 1 is 0, but ln of t goes to infinity as t goes to infinity. So since this value is equal to infinity, what we have here is that this limit is divergent, or this integral is divergent. Okay. So actually, what's interesting here is that if we compare this with the earlier example, we showed that the integral from 1 to infinity of 1 over x squared, right, was the example we worked out earlier, dx, when we got, this is the limit as t approaches infinity of the integral from 1 to t, which when we evaluated that integral, we got 1 minus 1 over t, and we showed that this is equal to 1. So this one is convergent. And this one's very similar, but notice it's just the integral of 1 over x. And this one is divergent. So there's a subtle difference, even though maybe we can imagine the shape of these graphs is very similar. And this is just a graph that's decreasing, going towards 0 as it goes to the right. And so the area of that region there is infinity. Versus this region here, so this is for the graph of 1 over x, versus this graph here is 1 over x squared. And from 1 to infinity, this area is equal to 1. So it's a bit of a weird comparison, that you would think that these graphs would be similar, but what we see is that for the 1 over x squared graph, when we go out very far to the right, that the tail end gets really, really tiny, and so essentially gets so tiny that the area towards in the tail end will contribute very little to the overall area, versus this graph where the tail end does not diminish quickly enough in order to get a convergent value. This one actually has an area that's infinite.